So how do you design a UV system? There are a lot of different types of UV systems. This is a random selection of things you can buy in the market. Some while ago, especially in America, these systems are quite popular, which are channel systems where you just put the lamp in a concrete channel and have the water flow through it. This is also one we get asked quite often by customers. We have a tank, can you just hang a lamp in there? And for many, also for me when I started my job, this looked really simple and cool and effective. This is actually one of the worst things you can do with a UV lamp, because as you know, that UV light doesn't penetrate far. So we see a nice blue light. All UV lamps produce some blue light, but the actual UVC light is a very thin area around it. So what happens here, you have a UV light in there. This breaks down some organic compounds, so in a way it produces nutrients. It produces a little bit of disinfection close to the lamp, so you also have dead bacteria. But all the rest of the tank is just illuminated with blue light. So you're actually breeding algae when you do this. We never have done this. We always say don't do it. It's much smarter to have a good, little, validated UV system circulating over the tank, so you know for sure you're only killing bacteria and you're not breeding algae or introducing nutrients into your water. And of course you can get really large ones with lots of lamps, and this one is ours, the chrome one in the middle, one of ours. And how do you start developing a system like this? It starts with a light field. Quite obviously, of course, you need to know how the light penetrates in the water you're meaning to treat. This is an example of one lamp, and we calculate for each point in a room how much light is left there. With one lamp, this is quite simple. If you have 5 lamps, you have overlapping areas, so the calculations become more complex. And if you would just assume a certain flow through the system, like an ideally mixed flow or a turbulent flow or a plug flow, you can quite easily calculate your average and your minimum dose. There are appliers, developers of UV systems that only do that. They calculate a light field, they assume a plug flow, and they say this is the average UVC and this is the average dose, and that's good enough. This is not the best solution because water doesn't flow like a plug flow always, or generally not. So how the water flows along that lamp is really important. This is the top example is a system from us. The bottom example is a more old school, easy system. And what we do is we do also calculate the hydraulics with CFD. CFD, Computational Fluid Dynamics, is a technology you can use, a model, to calculate how water flows through a body. In this case, you have the inlet here. The water sort of goes on the top of the reactor really fast, goes out really quickly, and the darker blue areas show where the water is slower. And what essentially happens is, one half of your stream races through the system, it goes along the lamp really quickly and goes out. So a part of that water is not treated enough. And the other part of the water, the dark blue area in the bottom, is almost stagnant. It's making little rounds again and again, so it's absorbing too much UV light. And too much is not a value, because you can only kill a bacterium once. So a dose of 300, if it's enough, you shouldn't apply more, because otherwise you're wasting energy. So these systems in general have a higher power consumption because they have to make up for the top part that raced through the reaction without absorbing too much light. The example I showed before, our system, we flow in from the bottom end. So the UV lamp, you can see it in the middle as the dark blue area, already makes the flow along the lamp ideal. And then we have a flow plate. You can see the holes, the little jets. And what we do is we make the water flow fast very close to the lamp, where the intensity is really high, so you need less illumination time to reach your dose. And the water far from the lamp, we make it flow really slow, so the intensity is much lower, but the illumination time is also much longer. And you can idealize that up to a point where your minimum and your maximum UV dose are very close together. And that means all your light is used the way you want it, reaching the similar dose. And this makes a big difference in efficiency. This is, I would say, the efficiency difference between these two approaches can be significantly more than 50%. So that's pure savings in energy. And that's important because the main operational aspect of UVC systems is energy consumption. So the lower you make it, the better your system is, the more sustainable your system is. And if you do this right, then you have a prototype drawing. We have a steel company, so they make, or we have a steel company, we work with a steel company, and they make the reactors for us in the Netherlands, which is nice because we can make a lot of different variations with different sensors, everything. But then you only have a prototype. You still don't know exactly in reality how it works. And in disinfection, it's already in the name, disinfection. You're taking away infection. So almost fundamentally, it's always a critical application. So you have to validate it. You have to measure to know what it actually does in biology. In the UV market, we use biodosimetric validation. It means you use active biology as a dosimeter. So you use biology, bacteria, standardized bacteria to measure the UV dose of the system while you disinfect it. And it's a quite elaborate method, but I'll try to explain it. It starts with buying spores of a bacteria or a virus in some cases. And you buy them at a specialized lab. We even once had a bacteria they took off a satellite, because satellites in space absorb a lot of UV light, so anything living there is quite resistant to UV. And because you sometimes want to validate a quite high dose, you need bacteria that have a linear UV response in the dose range where you want to be. So if you just use E. coli and at 200 everything is dead already, you can't validate a system with a dose of 400 joules or 600 joules with it. So we have a setup with a UV light. We put a petri dish under it with the biodosimeter we bought, so the bacterium. And we apply a number of UVC doses so we can make a reduction line. At a lower dose you have a reduction of 1 log, at a higher dose you have a reduction of 4 logs, and this line needs to be as straight as possible. It needs to be straight within certain constraints to be usable. And the norms that consider validations have numbers for all of it. So how straight does your line need to be? How steep can it be? How much deviation you can have between points and which points to choose. These are all captured in norms and standards we use in Europe. But this is only the first step. This step is only to measure how UV sensitive that one bottle of spores you got is. Because that sensitivity changes every time you buy a new bottle, even if you buy a new bottle from the same lab. So this is just to have your calibration line. Then you inject those same bacteria in a system. And also here, a number of things are important. You first have to mix it well, of course. You have to disinfect it first, because you only want to measure the bacteria you add. Then you add the bacteria, you let the UV reactor do its work, and you take samples before and after. And what you hope is that you have a nice plate of one organism coming in, and you don't have a plate of a lot of other stuff coming out. And in an ideal case, of course, the plate coming out is empty. There's growing nothing. That's not always the case, because for validation you also need to do a low dose, a medium dose and a high dose. So you know when the plate starts becoming empty, because if you count nothing, you count nothing. And in science, that's not a usable value. So you take lots of samples. This is an example of when we did 4 systems in our lab. And we had to plate out, I think, more than 800 plates. We don't do that. We have a deal with a lab in the neighborhood, so we just bring the bottles and they plate it out. But you have to count every colony, you have to count every dilution, you have to count every transmittance, every dose. And all these values together, if they are within certain statistical constraints, produce a validated system. And these realistic considerations, again, are very important. It's not just how much you kill, it's also how much power is your lamp outputting. The European method says you have to use a lamp that produces an intensity you expect at the end of a life. A lamp drops in power over 1.5 years, around that, 18, 16,000 hours, 12,000 hours, to about 80% of its original output. So you validate with your end-of-life lamp at 80% efficiency or output. So you know for sure that if you buy a new system, at the end of your lamp life, it's still disinfecting the way it should be disinfecting. Of course, you have to use sensors. You have to prove they're stable, they're precise, everything else. How is your lamp positioned? All these things are generally integrated. Not always is it integrated how hot or cold the water is. This also has an influence on the lamp power, or how dirty the system is. But the European validation norms do take these into account in how they translate it to an applicable system. So these are considered and measured to some degree. And in the end, you have the log reduction of the system you tested in the lab, the big system. You have your calibration line, and you can put these over each other and couple them. And if you really reach 2 log in your dynamic system, you can put it in your calibration line. That turns out to be 400 joule, and then you use the biodosimeter while disinfecting to prove a UV dose. And then you have a system according to a norm. This is the Dutch norm for drinking water. It says treatment of water with UV device shall yield a reduction of 400 joule at a wavelength of 254 nanometer. A reduction equivalent fluence. So the fluence, the power of the lamp, is coupled to a reduction of your organism. There are many more in Europe. The most strict one is the EU norm. We use it too. And then you really know what your system is doing.